This video is over section 7.5, which is the dot product. The dot product is a special type of product of vectors. So we'll compute the dot product, we'll find the angle between two vectors. So now these vectors have moved, and then we will find work. The dot product is represented in this way, and it's important to not be confused that this is multiplication, because it's not. But the dot product results in a number. It's not a vector, so it results in a scalar. And basically, what you'll do is you'll multiply the vertical component, or I'm sorry, the horizontal components, and then add it to the product of the vertical components, which is shown right here. It's pretty straightforward, so let's give it a shot. So we want to find the dot product of V and W, or V dot W. So this will be -2, so this value plus, or this value times this value, -2 times 3, plus this value times this value, 2 times 14. This gives me a -6 plus 28, which is 22. So the dot product here is 22. Here we will just take vector V dot vector V. So -2 times -2 plus 2 times 2. This gives me 4 plus 4, or 8. Same thing here. This would be 3 times 3 plus 14 times 14. So this just results in, this is 9 plus 196, or 205. Okay, now the dot product is helpful because we'll use it here in a little bit, but we need to be able to understand different properties of the dot product. Here they are. So you can pause this and see what you have. But one thing is V dot W is the same thing as W dot V, because it's basically a sum, and the order in which you add numbers doesn't matter. So here are just some different properties. Okay, so go ahead and pause the video and see if you can do this. So for part A, I want to find the dot product of V and W. Now this again is the dot product and not multiplication. So this will be -2 times -3 plus 6 times -1, which is 6 minus 6, or 0. Now in B, notice that I have V dot W and W dot V. Well, these two should be equal to one another according to the property on the previous slide, the first one. So this is also 0 based on property 1 of dot products. Part C would be found by taking -2 times -2 plus 6 times 6, which is 4 plus 36, or 40. Finally, D, or the magnitude of vector V, is -2 squared plus 6 squared, all under the radical, which is the square root of 4 plus 36, or the square root of 40. This breaks down into a perfect square 4 times 10, or 2 root 10. So nothing crazy, not too bad. But here's how we're going to use the dot product. Now, what we're going to want to do is we're going to want to find an angle between two vectors. But the problem is, previously, one of our vectors was here, so we were looking for this angle. But now the vectors have moved, so we want to find the angle between the two vectors. So it becomes a little bit more complicated. So to find this angle between the two vectors, we have this formula here. And typically I just use this formula, and then to find theta, I'll just take cos inverse of both sides, which is what this is here. Okay, so basically what we have is the dot product of the two vectors divided by the product of the magnitudes of the two vectors. So let's give this a shot. Okay, so it says to find the angle between these two vectors. So we want to find theta. So let's just jot down the formula that we had on the previous slide, which is cosine of theta is equal to the dot product of v and w divided by the magnitude of v and the magnitude of w. Okay, well, we should be able to find the dot product because we just did a ton of examples with it. So I'm going to take -2 times 3 plus 3 times 4. That will give me the dot product over the magnitude of each of these. Well, we should probably take a moment to find each of those magnitudes. So to find the magnitude of v, we've done this a gazillion times. We'll take -2 squared, which is 4, plus 3 squared, which is 9. This gives me the square root of 13. So the magnitude of v is the square root of 13. The magnitude of vector w is 3 squared plus 4 squared, which gives me the square root of 25, or 5. Okay, so I have plugged in everything that was needed into the formula. Now I'm just going to use some algebra to simplify. So the dot product is -6 plus 12, which is a positive 6, over 5 root 13. So this becomes cosine of theta is equal to 6 divided by 5 root 13. To solve for theta, I need to take cos inverse of both sides. So theta is equal to cos inverse of 6 divided by 5 root 13. Now, since the directions say round to the nearest tenth of a degree, we need to make sure we're in degree mode. When you plug this into your calculator, you should get approximately 70.6 degrees. This is the angle that is in between the two vectors. Go ahead and pause this and see if you can do this one on your own. Okay, so we know we need to find the dot product and the magnitude of each of these. So I'm going to find the magnitude first, just so we have it out of the way. So this will be 5 squared plus 1 squared, or I'm sorry, -1 squared, which is root 26. And then the magnitude of w is -5 squared plus 12 squared. This is the square root of 169, or 13. Okay, so we have the magnitudes. Now we need to find the dot products, and that will give us cosine of theta is. So here's the formula, just in case you wanted to see it. Okay, so the dot product is 5 times -5 plus -1 times 12 all over root 26 times 13. This is negative 25 minus 12 gives me a negative 37 over 13 root 26. So we will take cos inverse of both sides. This needs to go into your calculator in degree mode. So theta is approximately equal to 123.9 degrees. Not so bad. This slide just kind of tells you a little bit about some things that we will see. It talks about the dot product and what the angle will end up being between. But one thing that is important is if you get a dot product that is equal to 0. If you get a dot product that's equal to 0, then you'll find that theta is 90 degrees. So basically, these guys create this right angle. So theta is a right angle. We say that these two vectors then are orthogonal. So if you get a dot product of 0, the two vectors create a right angle, and they're known to be orthogonal. Now, so that's stated here. Now, vectors can also be parallel, and these vectors will be parallel if the dot product is equal to the product of the two magnitudes or the opposite of the product of the two magnitudes. So basically what you'll do is you'll find the dot product, you'll find each of the magnitudes and multiply them. If they're equal or opposites, then the two vectors are said to be parallel. So let's see what this means. In this example, it says determine if the given vectors are orthogonal, parallel, or neither. Well, if you're working and you find a dot product of 0, so dot product of 0, then you're done. They're orthogonal. If you get a dot product that is not 0, then you'll want to proceed, find the magnitude of each, then multiply those magnitudes together, and if it's the same as the dot product or opposite of the dot product, then they're parallel. If neither of these cases exist, then the two vectors are neither orthogonal nor parallel. Okay, so the first thing I would recommend doing is finding the dot product. Because if the dot product is 0, you can stop. So the dot product here would be 1.8 times negative 9 plus 0.3 times negative 1.5. When you multiply this, you get negative 16.65. Now, this is not equal to 0, so I can conclude that I know this is not orthogonal. So these two vectors are either going to be parallel or neither. So in order to proceed, now I need to find the magnitude of each of the vectors. So first, let's find the magnitude of k. We'll take 1.8 squared plus 0.3 squared, and this gives me the square root of 3.3. And I'm just going to leave that as the radical because it will come out messy. All right, now I'm going to find the magnitude of s, which is the square root of negative 9 squared plus negative 1.5 squared. This gives me the square root of 83.25. Same thing, I'm going to leave it under the radical. Okay, now if I multiply these, if I get either a negative 16.65 or a positive 16.65, then these vectors are parallel. If I get anything else, then the two vectors are neither. So I'm going to go ahead and take the magnitude of K and multiply it by the magnitude of S, which is the square root of 3.33 times the square root of 83.25. Plug this into my calculator and I get 16.65. Therefore, these two vectors are parallel. All right, same problem, just different notation. So first thing you want to do is find the dot product. So remember, the dot product BA is the same thing as A dot B. So either way is fine. So when you find this, you'll have 15 times 2/3 plus 5/6 times -12, which is 10, plus a -10, which is 0. Since this dot product is 0, we can conclude that these vectors are orthogonal. So these two vectors, if they were graphed, will create a right angle. Go ahead and try this one on your own. Okay, so in this case here, if you want to find the dot product, finding the dot product here, you should end up with a dot product of -60. Okay, well, this is not equal to 0, so it is not orthogonal. So you must go on to find out if they're parallel or not. So the way you do that is find the magnitude of R. This will give you the square root of -6 squared plus 15 squared will give you the square root of 261. Then find the magnitude of S. The magnitude of S is the square root of 5 squared plus the square, or plus -2 squared, which gives you square root of 29. Okay, so now what I'm going to do is I'm going to multiply these, which is the square root of 261 times the square root of 29. If I multiply these, I get 87. 87 is not -60 or the opposite of that. So this tells me that these two vectors are neither orthogonal nor parallel. Sometimes we will use vectors to compute work. So if D represents the displacement or the movement vector of an object from point A to point B under a specific force, so if something's being pushed or pulled at a certain force, the way we will find that is by using this formula here. So work is basically the force times the distance moved, or the displacement. So this piece here represents the magnitude of the force in the direction of D. This represents the distance moved. So to simplify it a little bit, this is the formula that we often use. Okay, and there's a little image here that you can kind of see. Basically, we're taking this object and we are pulling it. So we're using a specific force, pulling it a certain distance. So here's a type of example that you may see. It says a force of 85 newtons is applied to move an object 20 meters horizontally. If the force is directed 44 degrees upward from the horizontal, find the work done in moving the object. Okay, so basically what is happening is, so it's similar to the picture on the previous slide. So we have this force applied, and it's moving the object horizontally 20 meters. And the angle theta is 44 degrees. And the force is 85 newtons. So we know the force is 85 newtons. We know that the displacement is 20, but more importantly, it's moving horizontally. So we want this to be a vector, so it's going to be 20i, and then theta is 44 degrees. Okay, so the formula that we're going to use to find work is the magnitude of the force times the distance moved times cosine of theta. So this will be 25 times, oops, I'm sorry, this will be 85. 85 times 20 times cosine of 44 degrees. Now, we're going to have to label this. So 85 is newtons, 20 is meters, so our final answer is going to be Newton meters. So multiplying this all out, we find that the work is equal to 1,223 Newton meters. And that's the final answer. Go ahead and pause this and see if you can do this one on your own. We should know that the force is 25 pounds. The displacement is 200 in a horizontal direction once again, measured in feet, and theta is 15 degrees. So applying the same formula that we had in the previous problem, we'll have 25 times 200 times cosine of 15 degrees. The force is measured in pounds. The displacement or the distance is measured in feet. It tells us that we want it to be in foot-pounds. So multiplying all of this out, we should get on our calculator 4,829.629. But it tells us that we want it to be rounded to the nearest foot-pound. So we'll round up to 4,830 foot-pounds. And that concludes Chapter 7.